Hello everyone. In today's presentation, we present our paper accepted in the 21st IEEE ASME International Conference on Mechatronics Embedded Systems and Application MESA2025, which has the title A Survey on Finite, Fixed and Prescribed Time Convergent Optimization Algorithms, a Control-Theoretic Perspective, presented by me, Usama Fouad Abdel, a PhD student at the Department of Mechanical Engineering, IUC Merced. First, we'll introduce the concept of finite time and fixed time convergent optimization algorithms, its importance in the machine learning and AI era. How can contour theory, continuous time modeling, Economy theory can help in analyzing and designing these algorithms. Next, we introduce the basic definitions and lemmas required to define the finite time stability from contour theory perspective. Then we introduce a unified approach in the third section, how we can transform an exponentially stable system to be a finite or fixed time stable system. Then we review the basic or the classical gradient flows in optimization algorithms and its asymptotic conversion properties. Then we take a sample from the survey paper to introduce some existing methods in optimization algorithms. So as we know, optimization algorithms lie at the heart of modern artificial intelligence and machine learning techniques, where in most applications we need fast and efficient algorithms for solving the optimization problem, particularly in machine learning application with large data sets, where that leads to larger problem instances and potentially large computational time. As a result, stochastic gradient descent (SGD) and its variants like minipath SGD, Adana momentum-based and accelerated-based algorithms has emerged as a choice. In the optimization algorithm literature, people start to use the continuous time modeling of these gradient flows or optimization algorithms because of simpler and elegant proofs can be obtained by leveraging the tools of Lyapunov stability theory. Despite the much progress, there is still two limitations in this continuous time modeling. First one is that analysis still focused on asymptotic and exponential convergence, and that is convergence as time tends to infinity. Then there has no few systematic studies on developing discrete time implementation of these continuous time models. The notion of finite time stability is initially presented by Pat and Bastian in 2000, where a system is said to be finite time stable if the trajectories converge to the equilibrium in finite amount of time, called usually the settling time. This settling time may depend on the initial conditions and can potentially grow unbounded as initial conditions go farther away from the optimal point. While fixed time stability is more conservative, where it's a stronger notion which requires the settling time to be uniformly bounded for all initial conditions. Some studies in the literature show that this finite time stable gradient flows, or what we call the rescaled gradient flows or signed projected gradient flows, despite its continuous time model, but its explicit discretization using the traditional schemes like the Euler and Rankota still preserve its finite time property. Now let's introduce the definitions and lemmas from control theory. Now suppose a non-autonomous nonlinear system given by equation 1 x equals f of t x, starting from some initial condition x of t node equals x node. This system is defined to be globally finite time stable if it's globally asymptotic stable and the trajectories of the system starting from any initial conditions equal 0 after some time t that is larger than t node plus tau of t node x node. Tau of t node x node is the settling time function it depends on the initial conditions of the system. So we can see that the trajectory is reached the equilibrium point at some time t that still depends on the initial conditions. In the Lyapunov sense, the system is finite time stable if there exists a monotopic, a continuously differentiable positive definite function v that satisfies where the derivative of the trajectory satisfies an equality in equation 3. If we choose c is positive, rho is between 0 and 1. If this equation is satisfied, then the system is finite time stable, and we can have an estimation of this settling time that still depends on the initial condition. Fixed time stability is stronger notion. The system is fixed time stable if the settling time function tau is upper bounded by some constant tau max. And in the Lyapunov sense, if we have a Lyapunov function where the derivative of this Lyapunov function satisfies the inequality in equation 6, where rho 1 between 0 and 1, rho 2 is larger than 1, then the system has a finite time, a fixed time stable origin or equilibrium point. And then the settling time can be estimated, and we can see that this settling time is irrespective of the initial condition. As a more strong or conservative notion, the system is called a prescribed time or arbitrary time stable if we can pre-design this upper bound of the settling time with no dependence on any system parameter or initial condition, using a predefined or pre-designed function, then the system is said to be prescribed or arbitrary time step. For the Lyapunov definition, if we have a Lyapunov function with inequality in 8, where Tb is the predefined or pre-designed time, convergence or stability time, then Tb minus T is like high gain high gain of the system. In this section, we present a unified approach that all the papers in the literature mentioned in this survey follow that unified approach, where we can drive the system from its exponential stability to be finite time or fixed time stable. So assume a system that equals x that equals f of x. F is assumed to be Lipschitz continuous, and we then review the exponential stability of the function. The system is exponentially stable if the norm of the states is upper bounded by some exponential function as shown in equation 10. And in the Lyapunov sense, if we have an inequality, a Lyapunov function that is bounded between k1 norm x square and k2 norm x square, and the derivative of this Lyapunov function is upper bounded by minus k3 norm x square, then the function is exponentially stable. Now assume the function f is Lipschitz continuous. We have a modified system. This modified system can be obtained by rescaling the function f by sigma f of x. This sigma is a map from Rn to R plus. Then if we define the scaling function as in equation 13, where sigma is eta norm f to the power minus lambda, lambda is chosen between 0 and 1, and eta is positive, then using this condition we can transform the system from being exponentially stable to being to be a finite time stable. Now, in addition to the Lipschitz continuous condition, if we add another condition as in equation 14, where the norm of f is lower bounded by mx norm x to the power beta, where m and beta are positives, with we redefine the scaling factor as shown in equation 15, then we can transform the system from being exponentially stable to be fixed time stable, where the states will converge to the equilibrium point regardless in the same in an upper bounded time regardless of the initial condition. We can prove that if we have a Lyapunov function, we take the derivative. The derivative will be partial v partial x dot. X dot is defined as sigma multiplied by f, but we already know that partial v multiplied by f because the system is exponentially stable will satisfy this inequality from the Lyapunov definition. And we can also obtain obtain another inequality by introducing the function sigma first, and then from the Lyapunov stability we know that the function v itself is bounded by k2x squared. So we end up with the equality in 17, which satisfies the inequality, the finite time definition of finite time stability, the Lyapunov definition. For proving the fixed time stability, we have the rescale function, scaling factor sigma, defined as shown in this equation. Again, we derive the Lyapunov function using the inequalities from the exponential stability of the function itself. Then we can end with this inequality that is equivalent to the fixed time Lyapunov definition. Now we review some properties of the classical gradient flows used in the literature. If we have a minimization problem, we minimize a cost function j. Theta n Rn is a variable to be minimized. We assume that the function j has at least a minimum point, and for the classical gradient descent algorithm, we have a continuous time gradient flow shown in equation 19, where theta dot equals minus gradient f of theta of t. This one is represent the continuous time model of the classical gradient descent, and it's known from the literature that if the function f is convex and with Lipschitz gradient, we can prove that the function f minus f star has a convergence rate of 1 over t, and it's easy that 1 over t is asymptotic. It means that f approaches its minimum as t approaches infinity. Then we have the accelerated gradient methods modeled by the Nesterov second order differential equation, where r over t is a vanishing damping term, gradient f is the driving force. It's known from the Nesterov theory that if f is convex, gradient is Lipschitz continuous. F minus f star then has a convergence rate of 1 over t squared, which is still asymptotic. We can prove that by defining a storage function, a Lyapunov function in this form, taking the derivative as shown in equation 24, and using the convexity property, we can proceed with in the equation and show that the storage function is decreasing with a rate of 1 over t squared. Both 1 over t and 1 over t squared for the classical and the accelerated gradient descents are asymptotic, and we obtain the minimizer as t approaches infinity. We can show the representation of this gradient flows as first order dissipative process is also a way for the representation of this perspective for representing the system. Where recent works explore modified gradient dynamics that ensure finite time or fixed time stability or convergence of the system. The second order algorithms, like for example the classical Newton method shown in equation 24, 28, where if we assume the function is strictly convex, that means that the Hessian is invertible and the norm of the gradient is radially unbounded. We can prove that this gradient, second order gradient dynamics is exponentially stable by defining the following Lyapunov function. Another optimization problem used in the literature is the equality constraint problem, where we minimize a function subjected to a theta equals b and equality constraint. If the function j is strong, convex, and smooth, there is a lot of studies in the literature that can prove the exponential stability of this function. If the function j is mu strongly L smooth and the A function, the A matrix is full rank, and AA transport is bounded, This condition means that there is at least a visible set that contain a non-empty and closed that contains a minimizer. We usually we use the augmented Lagrangian as uh, perspective formula. We reformulate the problem as augmented Lagrangian, as shown in equation 32, and we end up with a primary dual gradient descent algorithm in equation 34, where the function f of omega is shown in equation 35. This gradient flow is can be proved to be exponentially stable, and we can take more details using the references in the paper. Now let's take a look at for taking some samples from the paper for the modified existing methods. For example, if we redefine the gradient flow to be as in equation 36, this is called a rescaled gradient. We can design or select or choose rho 1 as larger than 2 and rho 2 between 1 and 2. And we can prove by including some optimization properties like the Polyak-Lohazovic inequality, which sets a lower bound for the change in the function value as a quadratic of the gradient. For example, by defining the following Lyapunov positive definite Lyapunov function, or taking the derivative and incorporating the Polyak-Lohazovic inequality, we can prove that the function satisfies the fixed time stability Lyapunov definition. Another well-known finite time convergent gradient flows is what we call the rescaled and the signed projected gradient. These two, especially the equation in 45, the signed projected gradient, can be analyzed in the framework of Fibilo or differential inclusion, because the right-hand side is discontinuous, and using the Lyapunov or the Fibilo framework differential inclusions, we can prove that this one is finite time stable. One of the interesting papers in the literature is the one shown here, which is a comprehensive paper considering the unconstrained optimization problem with fixed time stability. This is the same gradient flow we just analyzed, the second order Newton method. This is a modified Newton's second order gradient flow that has the fixed time stability convergence property. In the same paper, they analyze a convex optimization with linear inequality constraints, a primary dual problem, and a min-max saddle point dynamics. For example, if the function is strictly convex, we have an invertible Hessian, and then the gradient will be radially unbounded. We can define a positive definite Lyapunov function as the half norm squared norm of gradient, taking the derivative because the Hessian is invertible. We can then proceed substitute for x dot, which is the defined gradient flow. Making use of the Polyak-Lohazovic inequality, we can end up with the Lyapunov definition of fixed time stability. This is another example where the function f is satisfy the Polyak-Lohazovic inequality. We can define the Lyapunov function f minus f star square, and we can proceed in the same with the same framework. In another paper, if we have a gradient flow scaled by the squared norm of the function f, if the function f is L-smooth, then and convex, then we can define the Lyapunov function x minus x star square. We can take the derivative. X dot is defined in 55, and using the L-smoothness and strong convexity, we can prove that V dot is less than a constant, which still satisfies the finite time stability conditions. Same for the case where lambda between 0 and alpha between 0 and 2. We can use the same framework to prove the finite time stability of the or convergence of this gradient flow. So while studying this survey paper, we show that The advance from asymptotic convergence of finite time, fixed time, and prescribed time shows a systematic improvement in optimization theory. These strategies can be effectively used in enhancing the algorithms in machine learning and AI. Other directions can be considered is the designing the algorithm to be robust against noisy gradients, but while maintaining the finite time convergence property, where this finite time gradients convergence of the algorithm can be um, extended to use in machine learning and AI applications, in addition to other applications like robotics, industrial processes, um, that will be valuable advancements. For the full references, we can visit the paper itself, and then thank you so much for the lesson.